Do you hear about that fucking object that's hurtling towards Earth at like 130,000 miles an hour?
No, that might solve all our problems.
Some intergalactic object that's there's this guy, Avi Loeb. He's a professor at Harvard that believes it might be an alien probe.
3i Atlas. And this time again, Avi Loeb saying some wild stuff about what this thing could be.
Because it's only the third time we've ever seen an interstellar object. And interstellar doesn't just mean Matthew McConaughey. It means something not from our solar system. It's interstellar. It's between suns. And so this thing came from like beyond our solar system and it's just passing through. It's only the third time we've ever seen something like that.
Is that why it's called 3i?
Yeah, because it's 3i, not 1i or 2i. It's 3i. That's exactly right. So it's exciting for that reason alone. And if it turns out to be a spacecraft, sure, I'll buy him lunch.
Imagine a comet traveling faster than anything we've ever seen, coming from the vast emptiness of interstellar space. No one could have predicted it, yet it's here. 3i/Atlas, the third object to cross into our solar system from beyond the stars. Its journey is one we could never replicate in our lifetimes.
This is not only an alien spaceship, but it's nuclear powered? Why are you saying that?
Well, thanks for having me. First, I should say that if the light that we observe from this object is reflection of sunlight, its size needs to be bigger than Manhattan Island, 20 kilometers or so. And there isn't enough rocky material.
What secrets does it carry from the dark, unexplored reaches of space? And what will it reveal about the universe we thought we knew? Space, in its vastness, can be difficult for us to fully comprehend. We find comfort in our cosmic neighborhood, the solar system, with its familiar planets like Jupiter, Mars, and of course Earth. We've become accustomed to what lies within this small region of the universe, but when we look beyond the solar system, we step into a whole new realm. Interstellar space. This is where the true immensity of the universe is revealed, and it is a cold, lifeless expanse that stretches out beyond the sun and the planets we know so well. Out there, over 18 billion kilometers from the sun, lies the edge of our solar system, where the heliopause marks the boundary between our solar system and interstellar space. It is in this zone of nothingness where the vastness of the universe really becomes apparent. Beyond the protective bubble of our sun's magnetic field lies an unknown and inhospitable environment, a place that has long fascinated scientists and astronomers alike. Only a few man-made objects have ever ventured beyond this boundary. The two Voyager probes, Voyager 1 and Voyager 2, are the only spacecraft that have crossed into interstellar space. Launched in 1977, these probes are still transmitting data, but they are far from being the only objects to traverse this space. In fact, in the past several years, we've been visited by two interstellar objects, comets or asteroids, that have entered our solar system from far beyond our cosmic neighborhood. These objects, Oumuamua in 2017 and Borisov in 2019, stirred excitement, raising questions about what else might be out there in the void of space. The first known interstellar object to pass through our solar system was discovered with surprising speed. Its elongated, cigar-like shape sparked countless theories about its origin, composition, and even the possibility of it being a probe sent by another civilization. It passed through the solar system too quickly to be studied in great detail, but it left an impression on the scientific community, leading to further investigations into the nature of interstellar objects. The second object, Borisov, followed a more typical path for a comet. Unlike Oumuamua, Borisov exhibited a more conventional appearance and behavior, but its origin from outside our solar system was still a remarkable discovery. The encounters with Oumuamua and Borisov were not just astronomical curiosities. They forced us to reconsider our place in the universe. These objects came from places far beyond the reaches of human exploration, and despite the excitement that their discoveries generated, these interstellar visitors have been relatively rare. However, just when we thought we were entering a period of quiet in our observations of such objects, a new discovery has brought our attention back to this phenomenon. In 2023, astronomers observed a new visitor from interstellar space, an object designated 3i/Atlas. This discovery has once again captured the attention of the scientific community, sparking discussions about the nature of this interstellar comet and what it can teach us about the universe. The object was detected on July 1st, 2023 by the Atlas Survey Telescope, a NASA-funded project designed to monitor the skies for potentially hazardous objects like asteroids and comets. The object was first identified as a moving space rock, but further investigation revealed that it had a hyperbolic and highly eccentric orbit. This is a key indicator that it came from outside our solar system. The Atlas telescopes, which operate in locations around the world, including Chile, South Africa, and Hawaii, have made significant contributions to the field of astronomy. These telescopes are part of the Asteroid Terrestrial Impact Last Alert System, a project focused on detecting near-Earth objects and other moving celestial bodies. The Atlas telescopes are particularly useful because they have the ability to survey the galactic plane, the bright disc-shaped region of our galaxy that contains much of its mass. This is a crucial area to monitor, but other survey systems, like Pan-STARRS, have difficulty photographing this region without encountering overexposure, which is why they avoid it. But thanks to Atlas, astronomers are able to scan this area without such issues. On that night in July, the Atlas telescope in Rio Hurtado, Chile, made a notable discovery. It spotted an object moving directly toward our solar system. Initially labeled A11, PL3Z, it didn't take long for astronomers to realize that this was no ordinary space rock. The Minor Planet Center, MPC, the international authority responsible for classifying and tracking minor bodies in our solar system, quickly took notice. They found that this object had already been observed by several other telescopes, including the Zwicky Transient Facility in California. As they sifted through the data, it became clear that this object was not just another asteroid or comet from our solar system. It had a trajectory that could only mean one thing: it had come from interstellar space. After confirming the object's interstellar origin, it was given the official designation 3I/Atlas, marking it as the third known interstellar object to be observed passing through our solar system. While its official classification was still under investigation, the object's coma, a glowing halo of dust and gas surrounding its nucleus, suggested that it was indeed a comet. This discovery also made it the third interstellar object we had encountered, following in the footsteps of Oumuamua and Borisov. The fact that 3I/Atlas had a coma wasn't just a small detail. It was an important clue that helped scientists narrow down its classification. Comets, unlike asteroids, are made of ice, dust, and gas, and their comas are formed when their ices sublimate as they approach the sun, creating a visible cloud of gas and dust. This feature made it clear that 3I/Atlas was more than just a random space rock. It was an active comet. Scientists were now left to wonder where this object had come from and how it had found its way to our solar system. The Atlas telescope system is particularly valuable because of its wide coverage. Unlike other telescopes that struggle to monitor the galactic plane, the bright, disc-shaped region of our galaxy, Atlas is specifically built to photograph this area. Other survey systems, like Pan-STARRS, often avoid this region due to the risk of overexposure, as it can be too sensitive to handle the brightness of the galactic plane. But with Atlas, astronomers can capture images without the problem of overexposure, making it an ideal system for finding objects moving through this dense part of the sky. On that fateful night in July, the Atlas telescope at Rio Hurtado in Chile made an intriguing observation. The telescope took 4 30-second images of the sky, all focused on a particular region near the Sagittarius constellation. The result was the detection of an object that appeared to be heading directly toward our solar system. The object, at first, was named A11+3Z, a code that didn't immediately give much information about its nature. However, as soon as the discovery was reported, the Minor Planet Center, MPC, in Cambridge, Massachusetts, took action. The MPC is the international authority on the tracking and labeling of minor bodies in the solar system, and it quickly began analyzing the object's trajectory and prior observations. What they found was both surprising and significant. The object had been observed before, not only by the Atlas telescope, but also by other facilities such as the Zwicky Transient Facility in California. These observations, dating back to June 14th, suggested that the object was not a typical asteroid or comet from our solar system. Its orbit was highly eccentric, and its trajectory revealed a hyperbolic path that could only mean one thing. This object was not native to our solar system. It had traveled from deep space, from beyond the boundaries of our sun's gravitational influence. Upon confirming the object's interstellar origin, astronomers were faced with another challenge: classifying it. Was it an asteroid or a comet? At first, the object appeared to be an asteroid, as it didn't show obvious signs of a tail or coma, the two main characteristics of a comet. But further analysis revealed something intriguing. The object had a coma, a halo of gas and dust that is typical of comets. This was a significant clue. As it turns out, when a comet gets close to the sun, the heat causes the ices in its nucleus to sublimate, releasing gas and dust into space. This produces a glowing halo or coma that surrounds the object, giving it a distinctive appearance. Given the presence of a coma, it was concluded that the object was, in fact, a comet. In light of this discovery, it was renamed 3I/Atlas, signifying that it was the third interstellar object to be observed in our solar system. The first two, Oumuamua and Borisov, had already made headlines, so the discovery of a third object brought new excitement to the astronomical community. Scientists were eager to learn more about this latest visitor from the stars, and to compare it with the previous interstellar objects. The name 3I/ATLAS also pointed to the involvement of the Atlas telescope network in discovering this object. The Atlas system is not only designed to find objects that could pose a threat to Earth, but it also plays a key role in tracking asteroids and comets that are too faint for other telescopes to detect. This unique capability of the Atlas system helped astronomers spot 3I/Atlas early, giving them ample time to study its path and characteristics before it passed through the solar system. What made this particular discovery even more exciting was the object's trajectory. As 3I/Atlas approached the solar system, its orbit was carefully measured, and astronomers were able to predict its path. The object's orbit was described as highly eccentric, with a value of around 6. In orbital mechanics, the eccentricity of an orbit describes how elongated or circular the path is. An eccentricity of 0 indicates a perfectly circular orbit, while an eccentricity greater than 1 suggests a hyperbolic trajectory, one that doesn't return to its point of origin. This made 3I/Atlas an object unlike anything we've seen before. It wasn't bound by the sun's gravity, and once it passed through our solar system, it would continue on its journey into the depths of interstellar space. One of the key factors that set 3I/Atlas apart from its predecessors was its speed. This comet was traveling at an incredible velocity of 58k seconds per second. To put this into perspective, that's like running the length of 580 football fields every second. This makes 3I/Atlas the fastest interstellar object we have ever observed, surpassing the previous records set by Oumuamua and Borisov, which were traveling at speeds of 26 km per second and 32 km per second, respectively. The rapid speed of 3I/Atlas meant that astronomers had to act quickly to gather as much data as possible before it passed through the solar system and disappeared back into the vastness of space. As the comet neared the sun, scientists became increasingly eager to understand where it was headed. Thanks to its highly eccentric orbit, it was clear that the comet would pass close to the sun at some point. The closest approach was set to occur on October 30th, 2023, when the comet would be at a distance of 1.4 astronomical units, AU, from the sun, just inside the orbit of Mars. This would place 3I/Atlas in a position where it could be observed closely by telescopes and other instruments. After this point, the comet would continue on its trajectory out of the solar system, back into the vast void of interstellar space. To learn more about the comet's behavior and characteristics, astronomers employed a variety of telescopes and observation techniques. One key observation was made by the Las Cumbres Observatory, LCO, a global network of telescopes specifically designed to observe transient astronomical events. These events can include changes in brightness or activity, such as those exhibited by comets. Using 2 telescopes based in Hawaii, astronomers monitored 3I/Atlas for signs of rotational variability, fluctuations in the comet's brightness that could indicate it was spinning on its axis. By studying these patterns, astronomers could determine the comet's rotation period and gain more insight into its physical properties. The LCO observations revealed that 3I/Atlas has a rotation period of around 29 hours, meaning it takes nearly a full day and a half to complete one full rotation. However, the variation in brightness was minimal, with only 0.2 magnitudes of change observed. This was a surprising result, as other interstellar objects like Oumuamua had exhibited more dramatic fluctuations in brightness. Despite the minimal variation, 3I/Atlas was still a relatively bright object, and its size was estimated to be substantial. Based on its albedo, a measure of its reflectivity, scientists estimated that the nucleus of the comet could be as large as 10 K in diameter, making it significantly larger than both Oumuamua and Borisov. As astronomers continued to observe the comet, they also noticed faint signs of activity. 3I/Atlas displayed a coma, a faint halo of dust and gas, which is a typical feature of comets. In addition, the comet was also found to have a tail, which spanned around 3 arcseconds across the sky. While the tail was relatively short, it was still an important feature to study, as it provided further evidence that the comet was actively releasing gas and dust as it approached the sun. However, the tail was often difficult to detect in images due to the prominence of the coma. The study of 3I/Atlas has only just begun, and it continues to surprise astronomers with its unique characteristics. One of the most fascinating aspects of this comet is its trajectory and the speed at which it is traveling. As mentioned earlier, 3I/Atlas is the fastest interstellar object we have ever observed. At a speed of 58 km per second, it is zipping through space at an astonishing rate, far outpacing previous interstellar visitors like Oumuamua and Borisov. To put this into perspective, this comet is traveling so quickly that it covers the length of approximately 580 football fields every second. This incredible speed makes 3I/Atlas a very different kind of visitor to our solar system, and it has left scientists eager to study it in detail before it passes through and heads back into interstellar space. Its velocity is a key factor in understanding its orbit and trajectory. As 3I/Atlas approaches the Sun, it follows a hyperbolic eccentric orbit that sets it on a path toward the outer regions of our solar system before it continues on its journey into deep space. A hyperbolic orbit is one in which an object's trajectory is so elongated that it will not return to the point from which it came, as opposed to an elliptical orbit, which would bring the object back again. This is a crucial detail because it suggests that 3I/Atlas is not bound by the Sun's gravity. Once it passes through the solar system, it will continue moving through space, never to return to our region of the galaxy. As the comet nears the Sun, its trajectory will bring it to its closest approach on October 30th, 2023, at a distance of 1.4 AU. Or about 1.4 times the distance from the Earth to the Sun. This places it just inside the orbit of Mars, and it will pass safely by Earth at a distance of about 1.6 AU that week, far enough to ensure that we are in no danger of any impact. In fact, 3I/Atlas will be approximately 600 times further away from Earth than the Moon, so there is no need for concern about any potential threat. But the key question is, what happens next? Once it has made its closest approach to the Sun, 3I/Atlas will continue to follow its highly eccentric orbit, veering past Mars and eventually heading back out of the solar system, on its way to the outer reaches of space. Astronomers have been closely monitoring 3I/Atlas using a variety of telescopes around the world, and the data they have gathered so far has provided some intriguing insights into the comet's characteristics. One of the key aspects of the comet that has been studied is its rotation. Using the Las Cumbres Observatory, LCO, telescopes, which are part of a global network designed to observe transient astronomical events, astronomers were able to track the brightness of 3I/Atlas over time. This allowed them to observe whether the comet was exhibiting any rotational variability. In other words, whether the comet's brightness fluctuated as it spun on its axis. Rotational variability is a common feature of comets, as the changing orientation of their surfaces as they spin can cause variations in the amount of light they reflect. The brighter areas of the comet's surface will appear more visible when they face Earth, while darker regions may reflect less light. By measuring these fluctuations in brightness, astronomers can determine the rotation period of the comet, as well as learn more about its shape and structure. The observations revealed that 3I/Atlas has a rotation period of around 29 hours. This means it takes approximately 29 hours to complete one full rotation. While this period is relatively long, the most surprising aspect of the data was the comet's light curve. The light curve, which is a plot of brightness over time, showed very little variation, just 0.2 magnitudes of brightness change during the 29-hour period. This was much smaller than the variation seen in previous interstellar visitors, such as Oumuamua, which exhibited much more dramatic fluctuations in brightness due to its unusual shape. Despite the relatively flat light curve, 3I/Atlas remains a bright object, and its size has been estimated to be around 10 km in diameter, which makes it significantly larger than both Oumuamua and Borisov. The size of 3I/Atlas is another important factor in its study. The estimated diameter of its nucleus, which is the solid core of the comet, is much larger than either of the previous interstellar objects. This suggests that 3I/Atlas could be more active than we initially thought, despite its relatively small changes in brightness. In addition to the coma and tail, further observations have shown that the comet is emitting a small amount of gas and dust as it approaches the sun. This is typical of comets, as the sun's heat causes the ices in the comet's nucleus to sublimate, releasing gas and dust into space. This process is what creates the characteristic coma, the glowing halo around the nucleus, as well as the tail that extends behind the comet as it moves through the solar system. The tail of 3I/Atlas has been a subject of interest for astronomers as well. When the comet was first observed, it was reported to have a tail spanning about 3 arcseconds across the sky. While this is relatively short compared to the tails of some comets, it is still an important feature to study. As the comet continues its journey towards the sun, its tail may grow larger and more prominent, providing astronomers with a better understanding of how the comet's activity changes over time. As of now, the tail is often difficult to observe because it is overshadowed by the coma. But ongoing observations will continue to provide new insights into this feature. In addition to the coma and tail, another interesting aspect of 3I/Atlas is its color. As with Oumuamua and Borisov, 3I/Atlas appears to be significantly redder than the sun. This reddish color is a characteristic feature of many comets and asteroids, and it provides further clues about the composition of the object. The reddish hue is thought to be due to the presence of organic compounds known as polycyclic aromatic hydrocarbons, PAHs, which are commonly found in space. These compounds may play a role in the formation of comets and other icy bodies in the outer regions of the solar system. As 3I/Atlas continues to move through the solar system, astronomers will continue to monitor its activity, brightness, and composition. Each new observation provides valuable data that can help scientists learn more about the nature of interstellar objects and the conditions in which they form. Given the rarity of such events, the study of 3I/ATAS presents a unique opportunity to explore the origins of these mysterious visitors and how they relate to other objects in our solar system. It also provides an opportunity to test some of the theories that have been proposed to explain the origins of interstellar objects like Oumuamua and Borisov. By comparing 3I/Atlas to these previous visitors, scientists can begin to develop a more complete picture of what these objects are and where they come from. The journey of 3I/Atlas is not just an exciting adventure in space, It is a journey of discovery. As it passes through the solar system, it is providing us with a wealth of new information about the cosmos and our place within it. We may never fully understand the origins of 3I/Atlas, but through careful observation and analysis, we can continue to unravel the mysteries of this remarkable comet. As it heads back into deep space, we can only imagine the secrets it holds, waiting to be uncovered by future astronomers and space missions. In the case of 3I/Atlas, astronomers have already gathered a significant amount of information, but there is still much to be learned. As it passes through our solar system and gets closer to the Sun, it's expected that more data will become available. One of the key areas of interest is the composition of the comet itself. Like Oumuamua and Borisov, 3I/Atlas appears to be different from typical solar system objects. Its trajectory, speed, and physical characteristics suggest that it comes from a region of space that is unfamiliar to us. But what exactly does that mean for our understanding of the universe? Could it provide us with insights into the early days of the galaxy, or even offer clues about the formation of our solar system? To answer these questions, astronomers will need to continue studying the comet's behavior and structure. One of the primary methods of studying interstellar objects is through their light curves, the changes in brightness as they move through space. The rotational variability of 3I/Atlas, which has been studied using telescopes like those from the Las Cumbres Observatory, has already provided valuable data. The minimal variation in brightness suggests that the comet may have a relatively smooth surface or a uniform composition. However, further analysis could reveal more detailed information about its surface features, such as whether there are active regions that cause spikes in brightness as they face the Earth. By observing how these light curves change over time, astronomers can continue to refine their understanding of 3I/Atlas and its characteristics. Another intriguing aspect of 3I/Atlas is its size. With an estimated nucleus diameter of around 10 km, it is much larger than Oumuamua, which was only about 800 meters long, and also larger than Borisov, which measured between 1 and 2 km. This larger size suggests that 3I/Atlas could be a more active object, with more gas and dust being released as it approaches the Sun. The presence of a comet and tail, which are typical features of comets, further supports the idea that 3I/Atlas is actively releasing material as it moves closer to the Sun. As astronomers continue to study its activity, they may be able to determine how much material is being released and how this process changes as the comet approaches its closest point to the Sun. The tail of 3I/Atlas has also been a subject of significant interest. While it is currently relatively short, measuring only around 3 arcseconds across, it is expected to grow as the comet gets closer to the Sun. As the Sun's heat intensifies, the comet's ices will sublimate more rapidly, releasing more gas and dust, which will result in a larger and more visible tail. By tracking the tail's growth and characteristics, astronomers can learn more about the comet's activity and the processes that drive its behavior. This will provide valuable information about the comet's composition and how it interacts with the solar wind and other environmental factors as it moves through the solar system. As 3I/Atlas continues its journey through our solar system, scientists are also considering the broader implications of its visit. The discovery of interstellar objects like Oumuamua, Borisov, and now 3I/Atlas raises the question of how many more such objects are out there. In fact, early estimates suggested that the density of interstellar objects in our galaxy could be quite low, with only one interstellar object per cubic astronomical unit of space. This means that such encounters are rare, and it may be a long time before we see another interstellar visitor. However, with advancements in technology and more telescopes being used to monitor the skies, it's possible that more interstellar objects will be detected in the coming years. As our ability to detect and track these objects improves, so too will our understanding of their origins, characteristics, and significance in the context of the universe. The study of 3I/Atlas also allows us to make comparisons with the two previous interstellar objects. Although Oumuamua and Borisov were both fascinating in their own right, 3I/Atlas has some key differences. For example, Oumuamua was an elongated object with a highly unusual shape, which sparked numerous theories about its origin and composition. Some scientists even suggested that it could be a probe sent by an alien civilization, although this theory has since been largely dismissed. In contrast, Borisov was a more typical comet, exhibiting features like a coma and a tail, and its composition was consistent with that of solar system comets. 3I/Atlas, while similar to Borisov in some ways, is larger and faster, making it an even more intriguing object to study. Its size and speed could provide clues about the types of environments where it originated, and the forces that shaped its journey across interstellar space. One of the most exciting aspects of studying 3I/Atlas is the potential for new discoveries. By examining the comet's composition, activity, and behavior, scientists can learn more about the conditions that exist in interstellar space and the processes that lead to the formation of comets and asteroids. For example, the fact that 3I/Atlas has a coma suggests that it contains volatile ices that have been preserved since the early days of the galaxy. Studying these ices could provide valuable information about the chemical composition of the materials that formed in the early solar system and the broader galaxy. Understanding the conditions that allowed these ices to survive for billions of years could help scientists learn more about the history of our solar system and the formation of planets, moons, and other objects. In addition to the scientific insights that 3I/Atlas can provide, its discovery also highlights the importance of international collaboration in space research. The observation of this comet involved telescopes and astronomers from around the world working together to gather data and analyze its characteristics. The Atlas network, which has been instrumental in identifying and tracking this comet, is a prime example of how global cooperation can lead to important discoveries. By sharing resources, data, and expertise, scientists can continue to improve our understanding of the cosmos and unlock the mysteries of the universe. As 3I/Atlas continues to move through our solar system, it serves as a reminder of how much we still have to learn about the universe. Despite our advanced technology and decades of space exploration, we are still only scratching the surface of our understanding of space. The discovery of interstellar objects like 3I/Atlas opens up new avenues of research and challenges our preconceived notions of the cosmos. It forces us to reconsider what we know about the formation of solar systems, the nature of interstellar space, and the potential for life beyond Earth.